anyone need help recalling how to do that? Okay. Recall that there's no classes on Monday for Labor Day. Okay, so don't come, no one will be here. I will be at home grading your damn labs. Nice big double stack I have with you guys as too. Forgot? Okay. Okay. Yeah, well, absolutely. So yeah, that's why I kind of wanted to reiterate what we did last time. So let's find data 3.129. So recall to go to chapter 3. And then scroll down. Chapter 3, section 1, problem number 29. So this is the hours worked for a sample of 25 students. Okay? A lot of this stuff, gosh, just about everything that we're going to talk about in chapter 3, all of these different numbers that we're looking at can be found under the summary stats function. Okay, so you go stat, summary stats, and then our data is in a column. So we go over to columns. Select the data. And then pretty much everything we need has already been selected under statistics. So everything that is hopped over to the right-hand side has been selected. We may want to go down to where it says mode. Let's see, I think we hit control and mode, and then the mode will be added on the right-hand side. I'm pretty sure that's how it works. We'll give it a shot. And then compute. Okay. So there's our mean. Looks like the average number of hours that this sample of 25 students work outside of home is 25 hours. Is that mu or is that x bar? Is it population data or sample data? It's sample data, right? This is a sample of 25 students. So think about where it came from, okay? It's a sample of 25 students, so it's x bar is the sample mean, and it's 20, is it 22 or 25? 22. What's our median there? What do we have, 20, 25? So what does that number mean, the 25? What does the mode indicate? Do you remember? Look it up. Anyone? Gotta know this, gang. Look back. Sorry?
The value that occurs with a single greatest frequency.
Is that the median or the mode? That's the mode.
And then the mean.
The number in the middle. Okay, so it means, okay, it's another form of an average, right? It's another way to think about an average. So how much data, how much of these hours are less than 25? How much data is smaller than this number? Half. Yeah, good. How much is bigger? Half. Yeah, so the median, remember, it's like the median of the road. Half on one side, half on the other. Yeah, Chris?
How does it calculate, or how do we calculate the median if there's like, say, a huge set of data that you can't just like visually get to the middle of? Like, you know how...
Use technology.
So there's not...
If you were doing it by hand, the first thing you would do is arrange it in order. Okay, you would arrange it in order, smallest to largest, and then you would, if there's an odd number of values, let's say there's, what were there, 25 values here? So you would go, let's see, 25 divided by 2. So we have numbers 1, 2, 3, all the way up to 25. Okay, so let's say that's an odd number, subtract 1, that's 24. Divided by 2 is 12. So we would have data values 1 through 12, and then we would have the 13th would be the median,
Uh-huh.
and then 14 through 25 would be, so the values, the first through the 12th, smallest of the values would be below the median, and then the other half, the 14th through 25th, is larger. So, and think about this all being arranged in order of smallest to largest, okay? So it's the value right in the middle, and if there's an even number, you take the mean of the middle two. It's the numeric average of the middle two, okay? So remember, the mode, the median is best for what kind of data? It's a better indicator of measure of center for, sorry? Skewed. Skewed data, good, good. It's the best measure of center when the data is skewed. Remember, the median is resistant, so it's not affected by unusually small or large values. Because we don't care, what these numbers are, right? We don't even know what they are. All we know is the one that's right smack dab in the middle. But that can have its weak points too, because then it's not representative. That number is actually not representative of the entire data set. So that's why most of the time as we proceed, we're going to be using the mean. Okay, do we have a mode here? The mode is 30. Okay. So what shape, okay, so the mean is smaller than the median, which is smaller than the mode. What's the shape of the distribution? This might be a question I'd ask you on a test. Look at the drawings we did last time. You should have that in your notes. Sorry? Good, left skewed. That mode, remember, is going to be that single greatest frequency, so we know that here's going to be the mode because it's got that highest frequency. And if the mean is smaller than that, and it's, there's not that much, this data isn't that, what do I want to say? It doesn't cover a huge range of values. So the fact that the mean is 8 units smaller, it means that there are some unusually small values out here that pulled it to the left of the mode. And remember, and think of that horizontal axis just like a number line, like smaller to larger, right? Okay, yeah, good stuff, you guys. And note that those people that don't work outside the home, boy, lucky slobs, right?
Did you say lucky slobs?
Lucky slobs? I'm joking, of course, but good for whoever doesn't have to work while being a student. Good for you.
Very lucky.
1, 2, 3 people don't have to work. So those small values probably are what pulled the mean toward the left end. Okay, polio. So going into measures of dispersion or spread. So think about that, just how's the data spread out? Let's talk about how the data is spread out and how do we measure that? And what values are used to measure that? Which ones are resistant? Remember, don't come Monday. Stay at home and do your stats homework. No. So the first measure of center is called the range. So the range is simply the largest value minus the smallest value. So the range just gives you the number of units that the data covers. Just you know, from the smallest to largest, this is how many units. That's it. It's pretty simple. The good part is it's easy to calculate. But the bad, part is it doesn't take into consideration all of the data. And the term lucky sloth, that's like old terminology.
I liked it.
Yeah.
It's all-
Are you gonna steal it, Jen?
I am stealing it.
So the bad is that it doesn't consider all the data, or take all the data into account. Is the range, would you say, is the range resistant? Is it, given how it's calculated, is it resistant to extreme values?
No,
No? How come? Why do you think no?
because like, if, you know, let's say like -3 is way out of the range, well, that's still gonna be considered the smallest value, and then, you know, 500 could still be considered the largest, even though maybe everything's between 10 and 20.
Yeah, there you go, because it uses the extremes. Yeah, exactly, good. Yeah, the range is not resistant because the two most extreme values are how it's calculated, okay? So it is not resistant. The next measure of center is the one we generally use, which is called the standard deviation. You can think of this standard deviation as the distance on average that each data value is from the mean. The average distance each data value is from the mean. It's a distance, so it's always a positive number. Well, actually, it can be 0, but that's a really trivial case. The standard deviation is found by, we have sample and population. The sample standard deviation is given by S. The population standard deviation is given by sigma. That's a lowercase sigma. And it just has like a little salute off the top of its head. Sample standard deviation is given by the square root of the sum of each data value minus the mean. You square that and you divide by n minus 1. The population is the sum of each data value minus its mean squared, divide by the population size. So here you're taking the distance between each data value and the mean. If it's population, that'd be the population mean, okay? Excuse me. Then we square those to make them all positive, okay? Because if the data value is below the mean, it's going to be a negative difference, right? So we square all those to make them positive. To take the average, we divide by the population size, right? Because if it's a population parameter, we're using the population size. And then we square root to get back out of that squaring. So like if our data were in meters, for example, we would have meters minus meters, and then that would be meters. Then we would square them, so we'd be in meters squared. Divide by a constant, we'd still be in meters squared. So the square root takes us back also to the original units of the data, okay? Let's talk about unbiased estimators. What we try to do, what we want to do in statistics is to make every sample statistic as close as possible to its the population parameter that it's trying to estimate. Okay? So like a population mean exists. We don't know what it is. We'll probably never know what it is. Excuse me. So, but we go out and gather sample data, right? And we take the sample mean, and it's kind of our starting point to estimating what's going on in the population. Now, what's the chances that that sample mean and that population mean are going to be the exact same number? Slim and none, but they should be really close. Okay, so what we find with the sample mean is the calculation of sample and population mean. Recall that they're calculated the exact same way. You just add up the amount, or I'm sorry, you add up all the data values and then you divide by the number of data values. In the case of the sample mean, it closely estimates the population mean with exactly the same calculation. Okay, that isn't so with the standard deviation, all right? The sample standard deviation tends to underestimate consistently the population standard deviation. So we divide by a number that's a little bit smaller to make the sample standard deviation just a little bit bigger, and thus a better estimator of the population standard deviation that it's trying to represent. Okay? So we have to just do a little adjustment in the calculation. These, as you can see, these calculations are not the same. They're going to be different numbers on the same data set. So what you have to do is be sure, if you have the population data, you want a population standard deviation. If you want sample data, you want a sample standard deviation. Okay? If you just the standard deviation that's given in your output in StatCrunch, that is a sample standard deviation. Okay, so you might make a note of that. That is the sample standard deviation. If you go to the summary stats command, like if I go back, I'll go options and down to edit. So in here you'll see in the statistics, where it has unadjusted standard deviation, that's the population standard deviation, unadjusted. So you might make a note of that, okay? And then we're going to also talk about the variance, and if you want the population variance, it is also the unadjusted version, okay? So again, those numbers are going to be slightly different, and you want to choose which one, you want to choose which one to use based on, do you have population data or do you have sample data? And again, 99% of the time we have sample data. So the value that you'll always find just in the general output is going to be a sample standard deviation. Yeah.
Can you say what was in the StatCrunch, like the options again? Which one each was? Does that
Sorry.
make sense? Like, which one's the sample, which one's the
Oh,
population?
sure. Just where it says the unadjusted are your population parameters.
Okay.
So the unadjusted standard deviation is this guy. And then if you scroll up and it just says standard deviation, STDDED, that's going to be your sample. And it's generally, I mean, if you just went into this menu and you clicked compute, you would get the sample standard deviation. Again, because we almost always have sample data as opposed to population. But be sure that if the problem says consider this sample or consider this population data, that you use the unadjusted. Okie dokie? Artichoke? Okay, so, let's talk about resistance. Is the standard deviation resistant, do you think? Is it resistant to extreme values, data values? What do you think? I wonder if the recycles in this place really go in a recycle. I always see weird stuff in the recycle bin. It's like, really? Who put that in there? That is so not
The
recyclable.
garbage men, they sort it out.
Do they? How would you like that job?
No, they have the sorters. I just know this because my dad's
Oh, it's okay.
Get into it.
No, that's
They
interesting.
sort it out, they have sorters. So they even go through the garbage and they pick out what's recyclables.
There you go. I am such a recycle Nazi, I'm crazy. Anybody that comes over to my house, like, okay, where does this go? So, resistant, yes, no?
No.
No? What do you think, Chris?
Because it takes into consideration the mean, which also has the outliers in it.
Okay, so the mean has all the, it uses the mean, which considers all the data. Okay, yeah, and what does the X in here stand for? You take each data value, all right, you subtract the mean. All right, same thing here, each data value subtracted, so it uses all the data. So your extreme values are getting into that calculation, therefore it is not resistant. You're right, it is not resistant. But that's another good way to look at it, is it uses another value that's not resistant. So kind of stands to reason. So standard deviation in either case is not resistant. The good thing about it is that it does take all data into account, or considers all the data. And you know, that's kind of its bad feature too. But I don't consider that to be a negative thing in terms of the standard deviation. Let's see, does it have a bad point? I guess if you do have really skewed data, it's going to really blow up your value of the standard deviation. But generally, the standard deviation is the measure of spread that we're going to use. So we generally use the mean and the standard deviation. There's another measure of center called the variance. Measure of spread called the variance. And the variance is just the standard deviation squared. Seriously, so the variance is just, and when you square a square root, what happens? What happens to the square root?
Cancels out.
Yeah, it cancels out, goes away. The variance is used most of the time in just derivation. It's in squared units, it isn't in the same units as the data, so we really don't use it very often, but we'll give it a holla. Give it a $2 holla. It is also not resistant for the same reason. And again, in your output, in StackCrunch, you will get, it'll say variance, and that's going to be the sample variance. To get the population variance, you're going to want to go to the unadjusted, which is right by the unadjusted standard deviation. What do you think? You guys okay? So this whole, the rest of this chapter, we're going to be looking at data and how it relates to one another. Oh, yeah. How does it, bless you. What is its relationship to the rest of the data? How can we look at different ways of measuring it against or comparing it to other data values in that data set? Let's go to So I hear there's a new pho restaurant up in, on Jefferson Street. Anybody know about that? Come on, you guys, step up. You gotta bring me all the food reviews. New restaurants anywhere? Anybody like? No?
Cheesecake Factory.
Cheesecake Factory? New Cheesecake Factory fan?
Never been there? I know.
A long time ago. I kind of tend to like the little local hole-in-the-wall places.
Randy's Bar and Grill in Kenesha's really good. So,
Randy's Bar and Grill. Anybody know that?
oh, they just changed it.
Yeah?
I think it's Evelyn's now.
Oh.
Yeah. the
Randy
last-
sold out to Evelyn, huh? Okay, let's look at data 3/2/17. Okay, well, I'll come back and report to you guys, how's that? Obviously, you don't like to eat the way I like to eat. You guys like to eat?
Oh, no, I love it.
Love to eat?
Yeah, what do you want? What do you
I
want
love to
us
eat.
do?
I don't eat to live, I live to eat. 17. Okay, so 3/2/17. Okay, here's some data, there are two different data sets for, and it's looking at the pH in tap versus bottled water, acidity. So, the lower the pH, the higher the acidity, isn't that the way it works? Yeah? So, you've got, basic is like 0, right? How does that work? Or no, that's 7.
So 14 is the most basic you can go, and 1 is the most acidic.
So 1 is the most acidic and 14 is
The most basic.
the most basic. We gotta make a note of this. All right. Bless you. It's a sneezy kind of time of year, right? Okay. So we've got 0, and we've got 7, which is, what do we call that, neutral?
7 is neutral.
Neutral?
There is no 0.
0 is more acid, and 14 is basic. Is that true? So pH is up there, right? It's like on the opposite end of acidic, is that right? Okay,
They're all
pH
pH
must be
values.
neutral.
what's that?
So like 0 is pH value, 7 is pH, so they're all pH
They're all
values.
Right, they're all measurements, but that's the most, the most acidic, right?
Basics.
And this is the most basic. Is that a better way to write it? You guys tell me. It's been a long time since I took a chem class.
I think
Like
he said it's a
forever.
bar on the bottom.
What's that?
There's no 0. There is no 0. It's 1 is the most acidic you can get.
Oh, you just go 1?
Yeah.
Okay. Okay, cool. See, we learn something every day, right? That's the way you gotta live. Gotta learn a little something every day. Okay, so, we want to compare the acidity in tap versus bottled water. So say, a company that bottles water makes a claim that, among other things, that their bottled water is less acidic. Well, I don't know, let's see. Let's compare them. So, let's see, this is, this is obviously a sample, right, because it's only 12 pieces of data. So let's find, let's find all of the sample statistics on the bottled and the tap water. Okay, we're gonna find the sample mean. We're gonna find the sample, do we know the sample size?
Yeah.
We already know that one, right? What did I say, 14? 12? 12. I'm not gonna worry about the mode. Let's find the sample standard deviation. Oh, you know what? Let's find the range. Let's find the standard deviation. That would just be S. And let's find the sample variance, just for giggles. Okay? If you have two data sets, you can calculate them both at the same time, the sample statistics. So we're gonna go to summary stats and columns. Just drag down and select them both. And I think if we look at all the stuff that's been highlighted on the left side, I think everything we want is in there. So the other values, you'll find that we'll use later in this chapter. So we're gonna learn more about comparing data. Okay, and it gives you the outputs just right together. Mean, tap water 7.5, bottled 7.5, what was the bottle? 5.2 is it?
Yeah.
5.2, okay, how about the medians? Bottled is, say? 5.22, so let's go 5.2 maybe, we'll just go one decimal place. How about the median of the tap? 5.5? 7.5. Range? What do we got? 0.6 and 0.2? Okay, thanks. Sample standard deviation, bottle. Do you see it?
0.08.
0.08? So the variance would be the square of that, right? So, standard deviation 0.08, square that 0.006. Compared to the tap, what do we got for the tap? Say? 0.15? Thank you. And then the variance? 0.003? 22? 0.002? Okay, so what do you think? So the mean acidity how would you compare? Yeah.
The ranges are switched.
Oh, okay, the ranges are switched. 0.2, 0.6.
0.3. Rounded.
0.3 this is?
Yeah, because it's 0.26.
Is that right? Okay, thank you.
The tap should be the 0.6.
Yeah.
The range.
The range is 0.6? Okay, what's that one?
Switch them.
Switch those.
Is that right? I keep you guys on the ball. Okay, so what do you think? If this bottled water says that they are less acidic, would you buy that? average, what do you see?
More
Is it-
acidic.
It's more acidic. It's actually more acidic. Do you see that? You guys, do you see that? Right? Because it's actually, the bottled water is going toward the acidic side, while the tap is actually going toward the base side, right? Maybe not that much of a difference, but it certainly isn't less acidic. Which data, the bottled or the tap, is more spread out? Which data is more spread out? The tap, why?
Has a higher
The
range.
number's bigger. The bigger the standard deviation, the more spread out the data. Just in a nutshell. Yeah, so the tap covers 0.6 units, while the bottled is only half of that in terms of range.
So like you could summarize, like the bottle is more acidic, but it is more consistent in its pH.
Perfect, yeah, that's a really good analogy, yeah. It's more consistent, yeah, the values are definitely closer together, yeah. Yeah, good one, good one. So that might be something I would ask you on a test. So, just tell me a couple things statistically about the comparison of these data sets. And you would use, well, the tap is less acidic. Why? Because its mean is higher, meaning it has more pH. Which data set's more spread out? Well, the tap, because the standard deviation is larger. So you guys, please take data. Take data 3-2-23. Oh no, take 3-2-24. 3-2-24, and find the sample statistics for that. So data 3-2-24. Oh, this is great. It's a local problem. This data is the